We have been discussing random vibration analysis of discrete multi-degree freedom systems. So, we will continue with that discussion and we will be concluding this discussion in this lecture, and we will begin discussion on random vibration of continuous systems. So, what we have done till now is that we have characterized the multi-degree freedom system through frequency response function and impulse response function. These functions now become matrices. So, for a n degree freedom system, the matrix of complex frequency response function is a n by n square matrix. It can be expressed in terms of structural matrices as shown here, or in terms of the natural frequencies, mode shapes and modal damping values as displayed here. Similarly, the impulse response function here becomes a matrix, a square matrix of size n by n, and this is determined in terms of the mode shapes, the damped natural frequencies, modal damping as shown here. The elements of this complex frequency response function matrix and impulse response function matrix are shown here, and we saw that they form a Fourier transform pair. This is to be expected because we saw similar relations being applicable for single degree freedom systems. The input output relation in terms of power spectral density functions is shown here. SFF omega is the matrix of power spectral density functions of the input. Input is modeled as a stationary vector random process with 0 mean. SFF omega is this power spectral density function. H of omega is the complex frequency response function matrix. Similarly, the matrix of covariance of the vector x of t1 and x of t2 is related to the matrix of the input autocorrelation function matrix through this relation, where here H is the matrix of impulse response functions, T is the transposition, star T is the transposition with conjugation. So, this is what we have discussed in the previous lecture. We began discussing about the action of earthquakes on extended structures, and we started talking about structures under differential support motions. This type of structures are typically found as piping structures in say industrial power plants, or also they are also associated with say long span structures like bridges, dams and so on and so forth. The main property here is that the support displacement here varies in space. That would mean for this structure that is shown here, there are 3 supports here. This is one support, this is other support, and this is third support. And in this illustration, we are considering the action of 2 support displacements at each of these supports. So, there are 6 support displacement components, and if we use, for example, finite element formulation to analyze this frame structure, at every node we can have 3 degrees of freedom, and this we call as the total displacement of the superstructure. So, the collection of these degrees of freedom is encapsulated in the vector ut of t. Ng we call is the number of support displacements. For this particular illustration it is 6, and n is the superstructure degrees of freedom, and in this particular instance it is 24 because there are 8 nodes 1, 2, 3, 4, 5, 6, 7, 8, and at each of these nodes there are 3 degrees of freedom. So, we have n is 24. So, we can write the equations of motion. If you write the global equilibrium equation here, the degrees of freedom can be partitioned as the superstructure degrees of freedom and the support displacement. These are applied support displacements. Based on this partitioning of the displacement vector, the associated structural matrices can also be partitioned. So, M, Mg, Mg transpose, Mgg, and similarly damping and stiffness matrices. Pg of T is the reactions due to the support motions at the supports, and Ut is n cross 1, Ug, Pg are all Ng cross 1, and Nt, which is the size of these matrices, is n plus Ng. Mck here are square matrices, whereas Mg, Cg, Kg are rectangular matrices, and in the analysis of this type of system of equations, we first find the so called pseudo dynamic response by considering only the static behavior of the system. So, if we consider now the static behavior of the system, we call the response as pseudostatic response. So, that superscript P denotes the pseudostatic or pseudo dynamic response, and the equilibrium equation is as shown here. So, this is the response of the structure simply due to the differential support displacements. There is no inertial actions or energy dissipation involved here, it is purely a static behavior, but still this equilibrium equation has to be analyzed at every time t. Therefore, the word pseudo dynamic is used to connote this fact. So, if we now write the equation corresponding to the first row, I get k into u p plus k g into u g is equal to 0. From this I can express u p in terms of k, k g and u g as shown here, and this matrix k inverse k g minus k inverse k g, I call it as capital gamma, and this can be viewed as a kind of a influence matrix. P g of t superscript p is the pseudostatic component of the reaction that can be obtained from the second row of this equation, k g transpose u p plus k g g u g is p g t. So, this has to be found after we solve for u p. So, this gives the pseudostatic reactions, this gives the pseudostatic or pseudodynamic displacements. Now, we split the total response into a pseudodynamic component and a dynamic component. So, moment we substitute this into the governing equations, we can derive now the equation for u of t, which is the unknown. U p of t has already been determined. So, the unknown here is u of t. So, if we now look at this equilibrium equation, wherever there was u t, I am writing u double dot plus u p double dot as shown here. Now, if I write the equation for the first row, I can get mu double dot plus mg into ug double dot and m into up double dot, c into this term plus cg into this term. Similarly, k into this term, kg into this term will be, I designate that as P effective t. So, this P effective t can be written in terms of the pseudostatic response and the ground support accelerations as shown here, acceleration and velocities. Now, for pseudostatic component of the response, I write u p is minus gamma u g double dot or plus gamma u g double dot. If I do that and rearrange the terms, the effective force gets expressed in this form. So, there is a kind of a mass matrix which multiplies acceleration, there is a damping matrix which multiplies the velocity. Gamma is a kind of a influence matrix that arises in computing pseudodynamic response. So, we can just examine the nature of this equation. Suppose if m is diagonal, that would mean mg is 0, because mg is a off diagonal component of the mass matrix, it is 0, and suppose C is proportional to stiffness matrix. In that case, I can write this C gamma plus Cg as say some alpha into k gamma plus kg. So, now for gamma, if I write minus k inverse kg, we will see that the contribution from this C gamma plus Cg becomes identically equal to 0, and the contribution from the second term to the effective force becomes 0, and the contribution from acceleration terms now read as minus m gamma ug double dot of t. Since ug is now a ng cross one vector, gamma will be a n cross ng matrix. Now, if all supports receive identical support displacements, then ng will be equal to 1 and ug double dot t will be a scalar function, and gamma would become simply a vector of units, and this equation reduces to the case of uniform support motion that we discussed in the earlier lecture. So, there is a consistency between what we are discussing here and what was discussed before. Now, let us now turn our attention to the problem of random vibration analysis, and we will begin by considering the analysis in frequency domain for steady state oscillation. This is a simpler is a simpler problem in comparison to time domain analysis, where initially there will be a transient non-stationary response, and if there is a stationarity it will reach that state as time becomes large. If excitation is non-stationary, of course, then we will have to deal with the problem in time domain. Now, now we will assume that UG of t is a vector of stationary random process with 0 mean and PSD matrix given by this SGG of omega. This is the PSD matrix for support displacement. Now, if you see the details of this forcing on the right hand side, we have velocity and acceleration terms. So, if we start modeling UG of t in terms of displacement power spectral density, then we have to deduce the power spectral density for acceleration and velocity, and we are ready with that, we know what it is. So, suppose P of t is this. Now, if you now take the Fourier transform of a truncated version of P of t, this is given by this. Here now we get Fourier transform of the displacement, although we have acceleration here, I will start working with displacements. Now, this is the Fourier transform of the effective force, and if its conjugate transpose is considered, we get this, we have to take transposition and conjugation, we get this expression. Now, if you want the power spectral density, you have to multiply this with this and apply this, take expectation and apply this limiting operation. So, if we now do that, SPP of omega is limit t tending to infinity 1 by t of Pt of omega multiplied by Pt star transpose omega. If I do that and carry out these simplifications, I get the expression for SPP of omega in terms of the power spectral density of vector of support displacements, the structural matrices and the influence matrix capital gamma. Now, moment I know the power spectral density of this quantity P of t, I can now use the standard input output relation in frequency domain. I get the output power spectral density function for u of t. This is a matrix given by h into SPP of omega, which is this long expression, and h star transpose omega, where h of omega is of course this, and in terms of MCK and in terms of modes it is this. Okay. So, this is a reasonably straightforward exercise. So, the only issue is you have to handle computation of power spectral density function for the effective force. You are given a model for support displacement and you have to deduce the power spectral density function for the effective force, and moment that is done, the standard input output relations take over and you get the solution. Suppose you are looking at only pseudodynamic response, UP of t is given by gamma UG of t. Therefore, the power spectral density function of the pseudodynamic response component is simply gamma SGG of omega gamma transpose, this is this. So, gamma is here is real valued, therefore, there is no need to conjugate and do that. So, this is the power spectral density of the pseudodynamic component. So, the total response can be written as pseudodynamic component plus dynamic component. So, this is gamma UG of t plus u of t. Now, therefore, if you now take the truncated Fourier transform of the total response, we get this, and if you now express ut of omega in terms of Pt of omega, I get Pt where Pt of omega is already determined. I can derive now the truncated Fourier transform of ut t of omega, and that is given by this expression in terms of ugt of omega. With this, we are ready to find the power spectral density function of the total response. Suppose if I call it as STT of omega, a few matrix manipulations will take us to this quantity. You can carefully discern that this total power spectral density function of the total response would obviously have a component due to pseudodynamic response and dynamic response, and a contribution from correlations between dynamic and pseudostatic response. Thus, suppose if you compute variance of the total response, it will have component from variance of pseudodynamic response, variance of dynamic response, plus a contribution due to correlation between pseudodynamic and dynamic responses. So, in the design of piping structures in power plants, it is necessary to compute these three quantities separately. So, we need to know the formulary for achieving that goal. Now, how about the analysis in time domain? So, we are back to this equation where P of t is the effective force as before, it is in terms of u g double dot of t and u g dot of t, and u g of t is a vector of stationary random process with 0 mean and autocovariance. We will now write it in terms of r g g t 1 minus t 2. This could as well be t 1 comma t 2 if it is non-stationary, but this is what we are using in this illustration. So, I have P of t 1 as this and P transpose of t 2 is transposition of this evaluated at t equal to t 2 and I get this. If I multiply these two and take expectation, I will get the covariance matrix for the vector random process P of t. So, if I do that, I get RPP of t 1 comma t 2, and in terms of the structural matrices and cross covariance, autocovariances between acceleration, support accelerations and velocities etc., we get this expression. If input is completely specified, it is possible to compute all these expectations, and once the autocovariance of the input is given, we now resort to the time domain relation for output autocovariance in terms of input autocovariance, and we get this equation. H of t is a matrix of impulse response functions expressed in terms of normal modes and natural frequencies and modal damping as here. So, if you plug that in, you have to carry out the requisite number of integrations and you will be able to characterize the response. Now, how do we compute these expectations? For example, you have to compute u g double dot of t 1 and u g dot of t 2 starting from autocovariance of u g of t. So, if you recall, we have shown that the autocorrelation between nth derivative of x of t and mth derivative of x of t is given by this, and if the process is stationary we get this. This can as well be generalized to find out this type of covariances. So, these are all matrices, each element of this can be for determined following this rule. This rule for example is applicable for two random processes x and y. Here we can as well replace x by y, this will become rxy. So, if there are two random processes, we can still use one of these two. If you are in transient domain, you have to use this. If process is non-stationary, you have to use this. If process is stationary, you could use a simpler version. Again, if you look at the total response, it has pseudodynamic response and a dynamic response. The up of t plus u of t, up of t continues to be gamma times ug of t. Now, this u of t can be given in terms of the impulse response function matrix and this vector of effective force. In principle, we have got the expression for up of t and you can take expectation of that, ut of t you can take expectation of that, you will get the mean. You multiply ut of t by its transpose and take expectation, you will get covariance of that, and so in principle this is eminently doable. Here again we can see that variance of total response even in transient state will have variance of pseudodynamic response plus variance of dynamic response and contributions due to correlation between pseudodynamic and dynamic responses. So, this in a way completes the analysis of multi-supported multi-degree freedom systems which are subjected to differential support motions. Now, we move on and consider the problem of random aberration analysis of continuous systems. So, we are moving to a new topic, but many features of what we are going to discuss now are quite similar to what has been discussed for discrete multi-degree freedom systems. For instance, the notion of natural coordinates can be generalized to continuous systems. The notion of frequency response functions and impulse response function matrices here become so called Green's functions. So, all those concepts are easily extendable for continuous systems, but it is worth going through this exercise. So, to start with, we can consider a situation where a continuous system serves as a adequate model to model an engineering structure. For example, if you consider a chimney, it can well be modeled as a cantilever beam, and if it is subjected to say wind load, this is the profile of the wind velocity. At ground the wind velocity is 0 due to the boundary layer effect, and as we climb up it reaches the atmospheric wind velocities, and this is again random in nature. So, this is snapshot of the wind velocity at a given time t, but on the other hand if you trace the velocity of the wind at a given elevation here as a function of time, it will look like this. This mean corresponds to this value, and the oscillations take place here about this mean due to turbulence. Now, this structure is immersed in a flow like this. So, due to this flow there will be a pressure field around the object, and if you integrate this pressure field over the surface area, you get the an effective force, and that can be resolved in the direction of the flow and perpendicular to that. We call that as this as drag direction and this as across wind direction. Now, the calculation of this pressure field can become somewhat more involved if this structure is flexible, in which case there will be an interaction between the vibration of this chimney and the pressure field around that, and these directions also keep changing. There will be an effective drag direction and effective across wind direction. In any case, the force field around this chimney will be a function of square of this velocity, and that will be a random process that evolves in time as well as along the height of the chimney. So, if you model this as a cantilever beam, we have to consider the dynamics of a cantilever beam subjected to a external force, say f of say z comma t, where f of z comma t is a random field which evolves in space as well as in time. Of course, the chimney can also be subjected to earthquake ground motion, although I have shown both these actions together, it is not implied that they are occurring together, not necessary. We seldom consider this type of situations, it is just for illustration I am showing. In the event of an earthquake, the supporting point here will be subjected to say actually 3 components also you can consider, 2 horizontal components of support displacement and 1 vertical component of support displacement. So, these again are each component can be modeled as a random process. So, then we have a continuous system where boundary conditions are time varying and they are modeled, the time variations are modeled as random processes. So, we need to consider, if you are interested in earthquake response analysis, the behavior of the structure under random time varying boundary conditions, and if you are interested in wind like situation, you have to consider the dynamics of say beams under external forces which are random fields in space and time. So, we will consider how we can tackle this problem, but before we get into the random vibration analysis, we will first review quickly a few important results from deterministic analysis of continuous systems. Another example is that of dynamics of a bridge like structure when a vehicle passes on the bridge. Suppose this is a railway bridge, this can be viewed as a simple model for a say a locomotive. Because of guideway unevenness, the passage of this locomotive on the bridge, there will be complex interaction between the irregularities here and the properties of this vehicle, and the effective force that gets transmitted, the wheel force that gets transmitted to the structure will be a random process, and this also is another example of random vibration of a continuous system where the bridge to a first approximation can be modeled as a beam. Of course, this is a hybrid problem where there is vehicle is modeled as a discrete system and bridge is modeled as a continuous system. This is one of these archetypal models for studying vehicle structure interaction. In the context of this problem, of course, there can be other sources of uncertainties. For example, the vehicle velocity and acceleration could be changing, they can be random. The vehicle payload, that is this mass itself, can be random, and of course, the damping and spring elements could also be uncertain in nature. Not only that, at any given time there can be more than one vehicle on the structure. If it is a highway bridge, if you take a snapshot of the bridge, a aerial photograph of the bridge, you will see that vehicles will be randomly distributed in space within the bridge and they will be moving in random directions if there are 8 line traffic for example, the direction and velocity of movement also will be could be random. So, it is a very complex loading system, and if we model this traffic also as a random process, then we have additional complexities. So, we will begin this discussion by conducting a quick review of dynamics of continuous system under deterministic excitation, and I select Euler-Bernoulli beam as an representative of these continuous systems. This could as well be an axially vibrating rod or a shear deforming soil layer, a plate or a shell. So, we will begin this discussion now. We will first consider the equilibrium equation for a statically loaded beam. This, if a beam property is varying with respect to space, the beam structure considered is shown here. This E I is a function of x and Q of x is the external load. The equilibrium equation will be d square by dx square E I of x d square y by dx square is Q of x. And the specified boundary conditions here, this corresponds to a, not to this beam, it actually corresponds to a structure which is clamped here and hinged here. This is the one example that I will be considering to illustrate the concepts. So, we will proceed with this. Now, if the same structure is now loaded dynamically, that means if this forcing function is a function of both x and time, in addition to the elastic forces, we also have now inertial forces and forces due to energy dissipation. So, this is the inertial force, and the damping forces are represented at two places. This is one term and there is another term here. This is a damping force which is proportional to the velocity of the beam. On the other hand, this is a force which is proportional to the time derivative of the bending strain. So, the general damping model could have terms proportional to displacement and proportional to velocity and proportional to velocity of the strain. So, we have included for the sake of illustration these things. Again, for this structure, that is that of a propped cantilever, the boundary conditions are displacement is 0 here and here, slope is 0 and bending moment at the hinged end is 0, and the structure could start with certain initial displacement and certain initial velocity. So, this is a field equation, this is valid for any boundary conditions, it can be a simply supported beam, free beam, fixed beam, etc. The field equation would remain the same. What would distinguish different beam types would be the boundary conditions, and together with the initial conditions, this forms the governing equations of motion. So, this is now a partial differential equation, it is a fourth order partial differential equation with y of x as a dependent variable, x and t as independent variables. So, we need to develop a strategy to solve this equation. So, we will try to now explore based on our experience with dealing with discrete multi-degree freedom systems. We will try to see now if we can perform a transformation of dependent variable and introduce certain new generalized coordinates such that in the new coordinate system this partial differential equation could become a set of uncoupled ordinary differential equation. That set will now be countably infinite, it will not be finite as in discrete multi-degree freedom systems. This type of systems are also known as distributed parameter systems, in the sense the if you take any chunk of the beam, it has elastic property, it has inertial property, it dissipates energy. Unlike in discrete multi-degree freedom systems where we used a mass and a spring and a damper, the mass element stored only kinetic energy, it had only inertial properties, there was no potential energy or stiffness here and so on and so forth. So, they are also known as distributed parameter systems. So, as in the case of discrete multi-degree freedom systems, we begin by considering the undamped free vibration analysis. So, this is the equation for undamped free vibration analysis. and we seek a solution in the form phi of x into t of t. So, this is a variable separable form that we are trying to see. We are not sure if this is possible. We have to first establish that such solutions are possible. We substitute into this, I get ei phi double prime t of t phi of x m of x t double dot t equal to 0. Here a prime denotes derivative with respect to x and a dot denotes derivative with respect to time. So, that t double dot of t is dou square t by dou t square. Now, if we divide both sides of this equation by phi and t, we get and perform some simplification. We can express this equation as on this part of the equation we have quantities which are functions of x alone. This is part of the equation where we have quantities which are functions of time alone. The variable separable form of the solution requires that these two ratios should be equal. Now, since this is a function of x alone, if I change x, only this quantity can change and this cannot change. Similarly, if I change t alone, only this quantity can change, this cannot change. Therefore, if these ratios have to be equal for all x and t, they have to be independently equal to a same constant. And if we now take that constant as omega square, I get for t of t a solution a cos omega t plus b sin omega t, and for phi of x I get an equation as displayed here. This phi of x is now the dependent variable, which is now the function of only space variable x. So, these are all ordinary derivatives now. So, the boundary conditions on y can now be expressed in terms of boundary conditions on phi. Y of 0 comma t is 0, therefore, phi of 0 into t of t is 0. If that has to be true for all t, phi of 0 must be 0. Similarly, phi of L is 0, phi prime of 0 is 0, and bending moment, that ei d square phi by dx square at L equal to 0. So, we get now a fourth order ordinary differential equation in phi of x along with the associated 4 boundary conditions. So, this is displayed here. You can see here that phi of x is a solution, phi of x equal to 0 is a solution, because you substitute phi of x equal to 0, this equation is satisfied and all the boundary conditions are satisfied. This is true for any value of omega. Now, trivial solutions are of no interest to us. So, we seek now to answer this question, can phi of x not equal to 0 be a solution to this for some values of omega. So, this is statement of the eigenvalue problem. Now, the operator is not a matrix operator, but a differential operator. So, to discuss this further, to keep the analysis somewhat simple, we will consider ei of x to be ei, m of x to be m, that means the beam is homogeneous, and if I now substitute make this simplification here, I can write this as ei phi 4 minus omega square m phi equal to 0, and if I divide both sides by ei and denote lambda to the power of 4 as m omega square by ei, I get this equation, and this equation can be solved. So, you can assume phi of x to be phi of x can be assumed to be e raised to sx. So, the characteristic equation will be s to the power of 4 lambda 4 equal to 0. So, you get 4 roots, s is plus minus lambda plus minus I lambda. So, associated with plus minus lambda you have sin h and cos h functions, with I lambda you have sin lambda x and cos lambda x function. For certain reasons which will become apparent, we will write the solution in terms of the function cos lambda x plus cos h lambda x, cos lambda x minus cos h lambda x, and similarly sin lambda x plus sin h lambda x and sin lambda x minus sin h lambda x. A, B, C, D are the 4 constants that we have to determine by using these 4 boundary conditions. So, to implement the boundary conditions, I need phi prime and phi double prime. So, a simple differentiation of phi of x once leads to this equation, twice leads to this equation. Now, imposition of boundary conditions. Now, phi of 0 is 0 and phi of L is 0. So, phi of 0 is 0 means if you now look at phi of x equal to 0, this will be non-zero, but all other terms are 0 at x equal to 0. Therefore, I get A equal to 0. That is particularly the advantage of writing the complementary function in the form that we have done. Phi dash of 0 is 0, therefore, I get C equal to 0. So, I am left with now two constants B and D, and to determine them I use the condition phi of L equal to 0 and phi double prime of L equal to 0, and this leads to two equations which are linear in B and D, and this can be put in the matrix form as shown here for B and D here, and for non-trivial solutions of B and D, the determinant of this coefficient matrix must be equal to 0, and that leads to an equation known as characteristic equation, and in this particular case you get tan lambda L is equal to tan H lambda L as the characteristic equation, and if you solve them you can get infinite set of roots. This is a transcendental equation, therefore, there can be infinite set of solutions, and these are known as characteristic values. Associated with each characteristic value there will be an eigen function, and that is displayed here, and sigma n is a constant that appears here is this. This type of these are the mode shapes for in this case a propped cantilever beam, but similar expressions for various types of single span beams like simply supported beam, free beam, both ends clamped, one end free, other end clamped, etc. They are widely studied and they are all catalogued in textbooks. So, for this particular case we get these constants Cn and sigma n to be this, based on which we can construct the mode shapes. If the beam is simply supported, the solution is somewhat simpler. The natural frequencies are given exactly by this, and the mode shapes are harmonic in space. I leave this as an exercise for you to prove this, and if you plot the mode shapes for different values of n, on x axis I have the span of the beam x by L normalized, and here I am plotting the mode shape. For n equal to 1 I get this red line, for n equal to 2 the blue line, n equal to 3 the green line, and so on and so forth. For the case of propped cantilever, the mode shapes can be sketched here. The first mode will be like this, the slope and the value of the displacement will be 0, that means the beam oscillates in this form in the first mode. The second mode will be something like this. So, you can construct this mode shape for higher modal values also. Now, again taking cue from orthogonality relations of eigenvectors that we encountered in dealing with discrete multi-degree freedom systems, we can now consider the question of, do these eigenfunctions satisfy any orthogonality relations. To see that, we consider two modes n and k, and consider the eigenpair omega n and phi n and omega k and phi k, and as per our formulation the eigenpair should satisfy these two equations. So, what I do is I multiply equation 1 by phi k and integrate from 0 to L, and multiply equation 1 by equation 2 by phi n and integrate from 0 to L. So, I get this at the end of that exercise I get these pair of equations. Now, if you now look at the integral that appears on the left hand side, if you do integration by parts, we can integrate once, I get 0 to L, ei phi k double prime becomes ei phi k single prime, phi k remains as it is. Then phi n, I have to now differentiate this phi n prime ei phi k double prime dx. Now, if I carry out this integration once more, I get this expression, this simplifies to this, and then I get this integral. Now, if you look at the nature of this integral for typical boundary conditions like a hinged end, a clamped end, a free end and a sliding end, we can see that, for example, if you consider a hinged end, the displacement will be 0 and this quantity ei phi k double prime will not be 0. If you arrest displacement, you get a reaction, and this reaction is a shear force. In a clamped end, the same is true, phi k is 0, there will be a reaction, shear force. How about at the free end? Displacement is not 0, but this quantity ei phi k double prime prime is 0 because there is no shear force at the free end. So, we see that the terms inside these two braces would cancel out, become 0 for any of the boundary conditions that we are typically interested in modeling single span beams. So, this integral therefore now simply becomes only this becomes 0, this becomes 0, I am left with only this. Now, we analyze this, a similar analysis will lead to a similar simplification for the second integral also. Now, based on that, we can show that phi n double prime of x and phi k double prime of x into ei of x integral 0 to L is 0 for n not equal to k, and m of x phi n of x phi k of dx equal to 0 for n not equal to k. These are the orthogonality relations satisfied by the eigenfunctions. Now, this second equation is similar to phi transpose m phi being diagonal, and this is similar to phi transpose k phi being diagonal for discrete systems. This transposition and addition are now of course replaced by integrations. So, in terms of mathematical content, these two are quite similar. Now, what is the use of finding undamped normal modes and natural frequencies? They should facilitate us to carry out forced response analysis. So, let us consider the problem of forced response analysis under specified initial conditions and specified boundary conditions. This epsilon x is now a constant that appears in modeling strain rate dependent damping, and c of x is a function that appears in modeling velocity dependent damping. We assume y of x comma t as n equal to 1 to infinity a n of t phi n of x. Now, phi n of x are known now, at this stage these are known. So, these are unknowns and these are the generalized coordinates. This phi n of x are the eigenfunctions that we have just now determined, and they satisfy these two orthogonality relations, with one with respect to ei and one with respect to m. So, ei is a function of x, m is a function of x, that is what is implied when I write ei inside this integral and m inside this integral. So, we substitute now this into the governing equation, this equation into the governing equation and I get the equation shown here. Now, for ei phi n double prime that appears here, I will write it as m omega n square phi n, because that is what is the definition of phi n of x. This epsilon x into phi n double prime right now I am retaining as it is, c of x is retained as it is, m of x is this, and this is f of x comma t, the external force. Now, as we discussed during while discussing multi-degree freedom system, discrete multi-degree freedom systems, we saw that the C matrix need to be restricted so that phi transpose C phi is diagonal. So, similarly here one of the model was C is equal to alpha m plus beta k. Now, this part of the model can be easily generalized to beam problem by considering this C of x, which appears here as alpha into m of x. This part of simplification can be extended generalized to continuous system by assuming that this function epsilon x is some nu times ei of x. So, that we will be able to now use orthogonality relations even for terms involving epsilon of x and c of x. How that happens? So, I will now write for epsilon of x nu into ei of x, therefore, that sits here, and this itself is now equal to m omega n square phi n, because ei x phi n double prime is m omega n square phi n, and this alpha mx remains as it is. Now, this is the equation that we need to tackle further. So, what we do? I multiply by phi k of x and integrate from 0 to L. If you now do that, I get these integrals. First term is m phi n is already there, m of x phi k phi n dx plus nu into a n dot omega n square m of x phi k phi n dx. Similarly, this c of x is actually alpha into m of x. This remains as it is. This is a n double dot of t m of x phi k phi n, and the right hand side I have 0 to L phi k of x f of x comma t d into dx. So, this will be a function of time alone, and now I can use orthogonality relations with respect to m. This is equal to 0 for k not equal to n, this is also 0 for k not equal to n, this is 0 for k not equal to n, similarly this is 0 for k not equal to n. So, only the case of k equal to n would remain, and I get the equation mn a n double dot plus some mn alpha plus nu omega n square a n dot mn omega n square a n is p n of t. So, where mn I have not mass normalized, so we will have to use this m of x phi n square of x dx. If the eigen functions are mass normalized, mn will be equal to 1. Right now we have not done that, so we are just leaving it as it is. So, for the generalized coordinates, I get this equation n equal to 1 to infinity. So, this can be cast in the standard form by writing alpha plus nu omega n square as 2 eta n omega n. So, this is now a family of single degree freedom systems with n running from 1 to infinity, and we know how to tackle them. We still need to find out the initial conditions to be applied to a n of t. So, to do that I have this y of x comma t is a k of t phi k of x. So, if you evaluate this at t equal to 0, I get a k of 0 phi k of x. Now, I multiply both sides by m of x into phi n of x and integrate from 0 to L. So, on the right hand side I get m of x phi n of x y of x comma 0. On the right hand side I get a n of 0 into m n, and this m n should be here, this must be equal to 0. So, a n of 0 is determined, a n dot of 0 is determined, and we are now into business because we have now uncoupled the equation, we have found out the initial conditions. So, I can integrate this. We know now what we know for single degree freedom system has to be applied for a large number of times, and we get that solution, and this is the final solution. This is the displacement field. Moment I know the displacement field, I can differentiate this. You want theta, that is the slope, is dou y by dou x. You want bending moment, it is EI dou square y by dou x square. You want shear force, it is dou by dou x of EI dou square y by dou x square. So, once y is known, I can find out all this, and once you know bending moment, you can compute the bending stresses. If you know the shear force, you can find out the shear stresses. You want principal stresses, you can do the analysis of state of stress at any point on the beam, find out principal stresses, principal directions, and you can check if failure criteria like von Mises failure or maximum principal stress failure criteria etc. are violated or not. So, you can do any engineering analysis that is of interest to you. Now, I will consider a few simple problems. Suppose we consider an undamped simply supported beam carrying a UDL. Suppose the load is suddenly removed, how does the structure vibrate? So, that means I have a beam which is carrying some UDL and it has deformed now, and this is the equilibrium equation for that, and now I suddenly remove the load. So, the structure has to oscillate, and that oscillation is essentially due to this prescribed initial conditions. The initial displacement profile is due to the applied load Q, and for T positive that load does not exist, therefore, the structure oscillates, and we assume that at T equal to 0 the beam velocity is 0. So, we can assume the modal solution as it is, and these are the equations. Now, we are considering undamped free vibration. So, A n of t is given by this, and initial conditions you have to utilize to find out these A n and B n. Initial velocity is 0, therefore, A n dot immediately goes to 0. So, B n becomes 0 and I am left with only a n, and these a n's can be found out by substituting this solution into the governing equation for y naught, and with a little manipulation you can find out all these a n's, and y of x comma t is given as here. A simple problem, you try it out, it will teach you some simple things very fast. Another problem somewhat similar sounding. Now an UDL is suddenly applied on an undamped simply supported beam. Determine the ensuing vibrations. Assume that the beam is at rest at t equal to 0. That means imagine some cement bag or something falls on a beam and beam vibrates. So it is a suddenly applied load. We use Hughes step function q u of t, and we initially the system is at rest. So I have given a few steps here. You can run through this and show that y of x comma t is indeed given by this. So this is an exercise that you have to complete. I will briefly touch upon another strategy to solve continuous systems. So to do that, we will consider a soil layer. Suppose this is a bedrock, and this is a soil layer characterized by shear modulus, mass density and some damping parameters, and this is the ground level. Suppose at the bedrock level I apply a unit harmonic displacement, and I would like to know what is the amplitude of displacement at the ground level, right. So this ratio is known as amplification factor, and if we are close to resonance, this amplification factor can be high, and this is of a fundamental interest in earthquake engineering problems to allow for local site conditions. So we need to perform the wave amplification studies. So this is a simple model. Suppose you assume that the soil layer behaves as a shear beam. You recall when we discussed Kanai-Tajimi power spectral density function model, I replaced this soil by a single degree freedom system. Now I am refining that model and I am replacing the soil layer by a shear beam. That means a beam that oscillates in this manner, u is this displacement, and this is the equilibrium equation, and I am assuming damping in a certain form with boundary conditions now on displacement as shown here. The top edge is free from applied tractions, therefore the strain there should be 0. So this is a boundary condition at the ground level, this is at the bedrock level. How do we solve this problem? We cannot directly use the modal decomposition method here, because to apply modal decomposition method we need boundary conditions which are not functions of time. This is a boundary condition, here boundary condition is a function of time, therefore we cannot use the eigenfunction expansion directly. There is a way to introduce a transformation of dependent variables to make the boundary conditions independent of time in the transform domain, and then subsequently apply normal mode expansion method. That I will consider in the next class, but now we will consider a solution to this problem in using a slightly alternative approach. This is a linear system and it is receiving input that is harmonic. So any response quantity is going to be harmonic in steady state at the driving frequency. That is one of the important properties of linear systems. So consequently what I assume is u of z comma t is some phi of z into exponential I omega t. This phi of z is the amplification factor dependent on z, it is a space and frequency dependent amplification factor. Now I can substitute the assumed solution, phi of z is unknown now, you substitute here, I get this equation phi double prime g plus I eta omega rho omega square phi equal to 0, and if I now introduce the notation lambda square is rho omega square divided by this, I get a equation. Here mind you the boundary conditions here are phi of 0 is 1, phi prime of L is 0. So this is not an eigenvalue problem, omega is a given driving frequency and the boundary condition here is non-homogeneous. So this is not an eigenvalue problem, it is simply a you have to find out what is the response phi equal to 0 is not a solution to this, because phi equal to 0 will not satisfy this boundary condition. So this is not an eigenvalue problem, although it has some resemblances to what we discussed earlier. So we put phi of z is a cos lambda z plus b sin lambda z. We have phi of 0 is 0, phi of 0 is 1 and phi prime L equal to 0. Based on that I get phi of x as cos lambda z tan lambda L sin lambda z. Now, if you now want solution at x equal to L, that is at the ground level, I get 1 by cos lambda L, and if I now substitute for lambda L, I get this, and where this nu star is the shear wave velocity, complex valued shear wave velocity, because it includes effect of damping under the driving frequency, we have got the amplification factor. Because at the bedrock level the applied amplitude is unity, and phi of L therefore directly represents the amplification factor. If you plot phi of L as a function of frequency, the amplitude of phi of L, you see that it has this characteristic behavior where there are several peaks which are uniformly spaced, and these are nothing but the points where these peaks occur are nothing but the natural frequencies of the soil layer. In Kanai-Tajimi power spectral density model, we included only this part, we had a single degree freedom model. So, this can be viewed as a preparatory step toward developing a Kanai-Tajimi power spectral density model, where soil layer is taken as a continuous system than as a single degree freedom system. We will stop this lecture here and we will continue with discussion on beams in the next lecture.